Welcome back to another video. Today, surprisingly enough, I'm back, I know. But today I'm going to make a video on the Lambert W function, okay? Or the W Lambert function, doesn't matter. The Lambert W function basically is a function that you use as an inverse operator. So you know how if we have, let's say, we have ln, and the inverse of it is e. So if we put ln to the ln of e, they would cancel out. And we have the same thing. Let's say we have sine of x, and we can take the inverse of it, which should be arc sine, and both of these would cancel out. And the same thing would be here. So the W Lambert function is, let's define it as f of x equals x e to the x. Okay? Now this, we can't just use the natural logarithm to isolate e or somehow drop down x. But what we can do is use the W Lambert function. And if we use it, okay, if we take the W Lambert of f of x, okay, which would mean we are taking the W Lambert of this part. When we take it, what happens is we only get the x. So it would be this. And that's the amazing property about it. And that's what we're going to use in our example. Okay, so before starting with the question, I decided to write a note here to show us what exactly we need to get the form into. So we need to get x e to the x. Okay, obviously x being any function. So I'm going to start off with the question. The question is simple. It's just 6 to the x plus x equals 4. It's that simple. The only problem is, as you can try as much as you want, but you're never going to be able to isolate the x. Because of this weird exponential form with this x here, it's just never going to work. No matter what natural logs you're going to use or any type of logarithms you're going to use, except the W Lambert function, okay? Because it simplifies this. It's what solves this question, and I'm going to show you this. So firstly, we're going to start off by minusing x on both sides, which gives us 6 to the x equals 4 minus x. Now the next step is interesting, because I mean, me personally, I never thought of doing this, but turns out you can divide the 6 to the x on both sides, and because of the properties of not logs, exponents, what you can do here is, if you guys remember anything from that from exponents, you know that 1 over, let's say, 4 to the x can be rewritten as 4 to the negative x. And that's what we're going to use here. So, that's what I'm going to do here. I'm going to add parentheses and rewrite this as 6 to the negative x. Okay, perfect. We are one step closer to this form. We have the 4 minus x here, okay? But we have a problem in this part, the e to the x. Firstly, we don't have an e. Secondly, this doesn't match this, but it could. You know how? We could use, again, exponents. So what's the thing here? What exactly are we going to use? Now, one of the properties of exponents is x to the m times x to the n gives us x to the m plus n. And that's what we're going to use here. So we're gonna multiply on both sides. Here we have negative x and we have this negative x, so we need the 4. So we're gonna multiply by 6 to the 4, to the positive 4. And we're gonna do the same thing here. 6 to the power of 4. Now obviously here it's gonna turn out to be 6 to the power of 4. 6 to the power of 4 times 1 is just 6 to the power of 4. And then here we're gonna get 4 minus x, 6 to the power of the 4 and the negative x combine, which gives us 4 minus x. Oh my god, that's perfect. We have the x here, but again, we need the e. So what do? We can rewrite this. How? Well, what we can do here is, I'm gonna just split it. Write 6 to the 4 equals 4 minus x, and then for this, I can rewrite it as e to the ln 6 to the power of 4 minus x. Why can we do this? It's because e and ln are inverse functions. So these in the end cancel out, which is exactly what we need. So since these cancel out, okay, no, actually the fact they cancel out isn't what we need. The fact that these cancel out makes it technically that this is the same as this, but written in a different way. And that's what's beautiful about math. So we can continue. We can, because of the property of logarithms, we can take down the 4 minus x down. So we're gonna get 6 to the 4 equals 4 minus x e to the 4 minus x ln 6. Okay. Again, this is amazing because obviously here some weird stuff is gonna happen. Like you can't add this, you can't make this match with this. So you can take down the 4 minus x and you're gonna get 4 minus x e to the 4 minus x, and then you have the ln x missing, ln 6 missing. And that's fine. Why? Because we can just multiply by ln 6 on both sides. Wait, no. On both sides, which in the end gives us 6 to the 4 ln 6 equals 4 minus x ln 6 e to the 4 minus x ln 6. And now this and this match. These two match, which is exactly what we need. Since now they match, what we can do is use the W Lambert function. And once we use it, I'm actually gonna erase this. Okay, so now I've rewritten it and erased everything. We go back to the form. 6 to the power of 4 ln 6 equals 4 minus x ln 6 equals 4 minus x ln 6. So now we know that this and these are equal, which gives us this. So now we use the Lambert W function. So we use it on both sides, obviously. And we know that this is an inverse of this form, which in the end, when we use the Lambert W function on this, it gives us x. It gives us this. So we're going to go down. We're going to have the Lambert W of 6 to the power of 4 ln 6 equals, and obviously this gives us just the inside part, the x, which is 4 minus x times ln 6. And now we just solve for x like we normally do. We divide both sides by ln 6. These cancel out and we get here ln 6. And then in the end we can just move the 4 to the other side. By moving the 4 to the other side, we're going to have W 6 to the power of 4 ln 6 over ln 6. And then by moving the 4 to the other side, it becomes negative here equals negative x. Then we multiply by negative 1 on both sides, which gets rid of the negatives here and gives us this. So in the end, solving this equation will give us x equal to this Lambert W of 6 to the power of 4 ln 6 all divided by ln 6 plus 4. And that's it for this video. A thing to mention is that the W Lambert function actually has it has two different versions. It has a version in the zero, I guess, world, and you have a version in the one world, I guess, a way to describe it. Each one of them gives you a different solution. So we technically have two solutions here for x, but usually you just go back to the 0, which is the one if you use, let's say, Wolfram alpha, if I got the name correct, it would default back to the 0, which is what we're gonna stay at. If you put this and use a calculator, or as I said, Wolfram alpha, you're gonna get something like 3.65, something along the lines of a decimal number. But in the end, this is in fact a constant, which is the cool part about it. It just uses this very interesting function called the W Lambert function. And that's it. I hope you enjoyed this video. I hope you found it interesting, and I'll see you in the next one. And if you have any problems with the way I explain stuff, drop it in the comments. This is annoying me. Drop it in the comments, and I'll see you guys in the next one. Goodbye.